Hi, good morning and welcome back to the next lecture of energy conservation and waste heat recovery. Today what we will do is we will move on to the topic of direct conversion devices. Okay. So, let me write that down and then we will see what we mean by that. So, the topic today, or actually a cluster of topics that we are going to discuss over the next few lectures, deal with direct conversion devices. Okay. So, what do we mean by this direct contact conversion devices? What is it that we mean by this? Now, imagine in a power plant when we get electricity out of that, how do we get electricity? Okay. In a power plant we have fuel that is burnt. So, let us say this is fuel. Okay. Then the fuel, when it is burnt, gives out thermal energy, which then goes to your power plant. Okay. Whereby out of where what we have is a turbine, right. So, we have a turbine here from where we generate mechanical work. Okay. So, the power plant we have thermal energy, from there we get mechanical work because of the motion or the rotating motion of the turbine, and then this turbine again is connected to a generator whereby we get electrical output or electrical energy. Right. So, what are we having? We are having thermal to mechanical, then to electrical, and in the process we are having a lot of equipments, like boilers, turbines, etc. in the power plant in this conversion from thermal to mechanical, and then again we have a generator from mechanical to electrical. Direct conversion. So, this is what we call traditional power generation, right. So, this is from fuel. In direct conversion, however, what we have is we have a source of thermal energy and which is directly converted to electrical energy. Okay. So, this is some device. So, this device can be of several types, and what we are going to discuss today is one of those. Okay. So, what I would say is this is the conversion, or let me say direct conversion device. Right. So, once again what we mean by direct conversion devices, let us say we have a source of heat, a source of thermal energy with us, okay. For example, some waste heat, which is the focus of this course, and we want to utilize that waste heat and the energy trapped in that waste heat to generate additional electricity. So, these direct conversion devices offer one means or one type of means by which we can convert the thermal energy directly to electrical energy. Okay. So, what we will do today is we will discuss one type of such direct conversion device, which is called thermoelectric generator. So, today what we will talk about is thermoelectric generation, also often called TEG. So, this is going to be the focus of our lecture today, thermoelectric generation. Again, this is a means by which, it is a phenomenon by which thermal energy can be directly converted to electrical energy without any moving parts or working fluids like what we need in a traditional power plant. So, again let us write it down that thermoelectric effect is a phenomenon by which thermal energy is directly converted. Okay. So, this directly word is very crucial here. So, let me underline that. It is directly converted to electrical energy and it can be the opposite way also. So, and vice versa. Let me write that down. Even though in this course we are concerned more with converting thermal energy to electrical energy, but thermoelectric can also do the reverse. Okay. And without any moving parts or working fluids. Okay. Well, for that matter, when we look at the other types of direct conversion devices, the same definition will hold good to a large extent. So, this is a very generic definition of what a thermoelectric generator can do without going into the details of its construction. Okay. So, to start with, what I will do is, as a teaser, I will play a small video here, okay, just to tell you what this is. Let us at this point not be concerned with what is there inside a thermoelectric generator. We will just consider it to be a black box, as we will see here, and this video shows a small experiment.
Small experiment. So we have thermoelectric module, the solid state device consisting of semiconductors connected by metal parts and sandwiched in between ceramic substrate. It's attached to the electric fan. We put it on the copper base, which would be the cold side, and it's just at the room temperature. And now we put the kettle with the hot water on top of the generator. Temperature gradients induce electricity in the module and thus make the fan rotating. This sounds like an excellent way to generate electric power. There are no moving parts, no working fluids, and it is very reliable.
Okay. So, what did we see in this video that we just played? What we saw was there was this device which we are calling the thermoelectric device. At this point, again let me repeat, at this point let us not be concerned about what is inside the thermoelectric device. The thermoelectric device, as we saw, came as a thin square square piece with what is called ceramic plates on both sides. And in this experiment, what was done was there was a temperature gradient that was created across the thermoelectric device. How did we create that? On one side there was a pretty big mass of copper, and we can assume it to be close to room temperature and an isothermal block. And on the other side, what the experimentalist did was he put a hot kettle with hot water inside. So, there was definitely a temperature gradient that was created across this thermoelectric module, and then as we saw, the module had two leads coming out of that, which was connected to a fan. So, as soon as the temperature gradient was created, we saw that the fan started running. So, what does it mean? It means that in a thermoelectric module, if we are able to create a temperature difference across the thermoelectric module, that is, we can generate electricity. Okay. So, it almost sounds like magic, right? I just had a small innocuous small piece. I maintained one end at a higher temperature, the other end at a lower temperature, and I was able to get electrical energy out of it, which was used to run a fan in this case. Okay. So, let us see, why is this happening? What is there inside a thermoelectric device which is leading to this phenomenon? So, to understand that, what we will do is we will go back in history a little bit and talk about something which is called Seebeck effect. Okay. So, Seebeck, what he did was, many years back Thomas Johann Seebeck, almost I would say close to 200 years back, what he did was, again this many of us do not know, he accidentally found this, by the way. He accidentally found that if we took a metal bar and if there is a temperature gradient across that metal bar, then he was able to show that there is actually a voltage that existed between the two ends of the bar. Okay. So, this is what Seebeck found at the beginning as an accident. Okay. And he worked on this finding a lot, and then finally what we know as a Seebeck effect today is that if two dissimilar materials, if you have two dissimilar materials that are used to make two junctions, and one of them is kept at an elevated temperature and the other one is kept at a lower temperature, then you will get, or we will get, a EMF or a voltage across the materials, right. So, again I repeat, let me write it down also. When two dissimilar materials are used to make two junctions, okay. If two dissimilar materials are used to make two junctions, one of which is heated and the other cooled, a resultant electromotive force or EMF is generated between the materials. Okay. And the most common application that we as thermal engineers utilize Seebeck effect is while measuring temperature through a thermocouple, right. It uses Seebeck effect, but let me write this down. So, let us say I have two dissimilar materials and one at temperature T1, the other at temperature T2, and let me denote those materials in this fashion, one by red color and the other by blue color. All right. So, let us say this is material A and this is material B, and what we are doing is, on one end let us say we are heating it up, the other end is maintained at a lower temperature. Then what we will see is, if we measure a voltage across any 2 points, let us say these two, I am going to measure an EMF or a voltage, which means that there is a current that is flowing through this. Okay. Seebeck also showed that we can write this EMF that is created is directly proportional to the temperature difference delta T, and the proportionality constant was named as Seebeck coefficient. Okay. So, this is the Seebeck coefficient. All right. So, the same thing is shown in the slide over here. Okay. Alpha AB, which is often denoted to often the alpha is used to denote Seebeck coefficient, from A to B is the proportionality constant that relates the amount of voltage that we are going to get or the EMF that we are going to create due to a temperature difference delta T. Clear? So, this is Seebeck effect. Now, hand in hand what happened was Peltier. So, let us talk about the next thing, which is Peltier effect. Peltier effect many a times is said to be just the opposite, which means that if a direct current flows through a pair of junctions of dissimilar materials, then a temperature difference is created across the two junctions, resulting in heat flow. Okay. Again I repeat that what it means is, if you have again two materials A and B. So, I am going to write it as A, I am going to write it as B, and let us say if we now have a current, a direct current flowing through this circuit from A to B. Okay, let me close the circuit, join these. Then what happens is, if a current is flowing through this, the same current over here, then what happens is, we see that there is a temperature difference that is created across the ends, say T1 and T2, okay, and let us say T1 greater than T2, and as a result of which there is a net flow of heat from the hotter junction to the colder junction. Okay. So, this is the reverse of Seebeck effect. Again I am not writing it down, let me repeat it again, that if a direct current flows through a pair of dissimilar materials, then a temperature difference is created across the two ends, across the two junctions, thereby resulting in heat flow from the hotter junction to the colder junction. Okay. So, here we are actually making the current flow and giving rise to a temperature difference, whereas in Seebeck effect the temperature difference was the cause and the EMF, and therefore, the current flow was the effect. Okay. So, this is how Peltier effect is often defined as, but actually what happened was, it is a little more involved. The Peltier effect, which says that when a current flows through a junction of two dissimilar materials, the amount of heat, and this is over and above Joule heating, because whenever you have a current flow you will have Joule heating, but there is an amount of heat over and above Joule heat which has to be removed or absorbed at the junctions to keep them at the same temperature, at constant temperature. Okay. And this additional heat which has to be removed, which is over and above Joule heat, is known as Peltier heat and is given by this expression. So, I will denote it as Q of A to B is equal to pi AB times current, and here again this pi AB is known as the Peltier coefficient. Okay. So, therefore, on one hand we have a definition of Seebeck effect and the definition of Seebeck coefficient, and here we have the definition of a Peltier coefficient, which relates the amount of Peltier heat that is generated due to a current flow across the junctions of dissimilar materials, and that relates it to the heat that is generated is related to the current that is flowing through the circuit that is formed because by these two dissimilar materials, and the two are related by the Peltier coefficient. Clear? So, now that we know what is Seebeck effect, what is Peltier effect, the last thing that we would just state here without any proof is that Peltier coefficient pi AB, let us say, is related to Seebeck coefficient alpha A to B. And how is it related? It can be shown that it is related in this form: pi A to B is equal to alpha A to B times T, okay, times the absolute temperature. Clear? And so, what is T? T is the absolute temperature of the junction that we are talking about. Clear? So, this is how it is related. Okay. So, with this background, let us move on a little bit and talk about what Seebeck found. Let us move back again and talk about what Seebeck first found accidentally. He found that when he took a metal bar and maintained a temperature gradient across the two ends, he was able to measure an EMF or a voltage across the two ends. So, why does this happen? Okay. So, now in hindsight, at that point it was an accident, but later it was also explained. So, let us consider a metal in this form, a metal bar. Okay. I am maintaining one end at a temperature T1 and I am maintaining the other end at a temperature T2, where I know that T1 is greater than T2. Okay. If this is the case, what happens? If this is the case, what happens is we have electrons, right? What are the current carriers or the charge carriers in a metal? These are electrons. So, let us say I have a lot of electrons everywhere. So, the electrons that are close to the hot end get more energized, and then they will start vibrating at a more vigorous rate compared to the electrons that are away, right. So, therefore, how does it work is, therefore, what happens is the electrons at the higher temperature end are more energized, they will start vibrating more vigorously, and net result is there will be an effective migration of electrons from the hotter end to the colder end. Okay. So, let me write it down. So, when it works is, how it works is, consider a metal block heated at one end. Okay. So, which is what? T1 greater than T2. So, then what happens? The electrons at the heated end are more energized. Clear? Why they are more energized? Because they have now higher energy because of the higher temperature. Okay. So, resulting in a net migration from T1 to T2, okay, and therefore, results in an EMF, electromotive force across the junctions or ends, across the ends, let us say. Okay. But however, keep in mind that this delta V or the EMF is minuscule. Okay. So, let us write that down also. However, this EMF for metals is minuscule. Okay. So, the Seebeck coefficient for metals is very low. So, if that is the case, what do we do if we want to have an appreciable EMF? So, one may argue that okay, why not take a bunch of these metal blocks and arrange them in series, so that the voltages add up. Okay, fair enough. Let us see what happens. So, I will take a bunch of these materials. So, let us say okay. So, this is scenario 1. Scenario 2, what is scenario 2? I will have a bunch of these metal blocks, let us say 1, 2, 3, 4, let us say 4 for now, and what I will do is I will maintain this end of all of them at a lower temperature and this end of all of them at a higher temperature. Clear? Okay, fair enough. So, therefore, definitely what I will get is I am going to end up with a positive voltage here and a negative voltage here, positive, negative, positive, negative, positive, negative. No questions about that, absolutely fine. Okay. So, the hotter end will be positive for all these metal blocks and the colder end will be negative for all these blocks. Now, the question is, how do we connect it in series? If you have to connect it in series, what we will have to do is we will have to connect them by conducting wires, the negative end to the positive end and so on. So, let us do this, clear. So, if we do this now, what happens? We have generated an EMF across these metal blocks, but however, these connecting wires are also metals, and because of the temperature difference across them, they are also going to give rise to a potential difference, and that EMF, that delta V or EMF or potential difference that is created will be opposite to the direction of the EMF that we have generated in these metal blocks. So, they are going to oppose. Okay. So, therefore, this arrangement will not work. So, let us write it down. So, if we join many such metals in series, okay, if we join many such metal blocks in series, the one that we saw over here, then what will happen is, the problem is the connecting wires will oppose the electron movement. So, the electrons, instead of going from here to here, will actually tend to come in the metal wire, or the connecting wire will tend to migrate from the hotter end to the colder end, thereby opposing the EMF that is generated in the metal blocks. So, therefore, this is not going to work. So, let us write down. So, will not work. So, we need to think of some other means, okay, not just electrons in metal blocks, but something else that we have to use as carriers if we have to use the thermoelectric effect for generating electricity. Okay. So, that is what we are going to cover in the next lecture. Okay. So, let us end here by so today what we covered is, we started with a small video of what thermoelectric effect is. Well, before that we talked about what is a direct conversion device. Then in the thermoelectric effect, we saw a small video where a thermoelectric generator was able to generate electricity simply by maintaining a temperature difference across its ends. So, we saw that it was almost magic, and then we said, okay, why is it happening? Let us look into that, and that is what we are doing now. We talked about Seebeck effect, we talked about Peltier effect, and in the next class we will continue our discussions on this. Okay. So, thank you very much and see you in the next class.